Happy Friday. All right, so today I have to confess is in fact one of my favorite parts of the whole course. So you guys better be good. Oh yeah. So I hinted on Wednesday that you really wanted to take the derivative matrix for a function and turn it on its side and make it into a vector, and then see what all the stuff we've been doing all semester will tell us. So we have, we're going to concentrate on functions that are real valued in Rn. I'm going to draw you lots of pictures today when n is 2, actually, so you don't have to be in 157 space. We have our formula I'm going to base most everything we do today on is the fact that if f is differentiable at A, then we have this beautiful succinct way of computing directional derivatives, namely df of A applied to the vector v, which I'm reminding you looks like something like this, where this is v, and this is df of A. So 1 by n matrix times a vector in Rn. Now, we've been saying this pretty much since the third week of the semester or so. We can think of that, of course, as being the dot product. If I take this matrix and I transpose it, then it becomes the dot product of that vector with v. So I'm transposing here. And so instead of having the partial derivatives at A going across this row, I've now got partials going down this vector. So this orange vector here is the transpose of the derivative matrix. And I suggested to you guys on Wednesday that this vector is so important we need to give it a name. So it's called the gradient. So the gradient of f at A is the vector that you get by transposing the derivative matrix. So that's the vector whose components are the partial derivatives and all of you guys who have seen some semblance of multivariable calculus before have seen this a lot and have never seen the other stuff we did. Right? Yeah. Okay. Now, I want to really emphasize today then our updated version of this formula. Again, I'm going to assume f is differentiable at A throughout the discussion today. Today is not a day about weird Math 3500 functions. It's a day about mainstream, real-world applications functions. So we're not worrying about weird stuff. We're assuming f's differentiable. Then we have our updated formula now, which says that the directional derivative of f in direction v at A is the dot product of this vector, which is called the gradient, and written with a nabla.
Is that an upside down delta?
It's an upside down capital delta. I don't know. It's one of these.
I don't think it's a language.
I don't think it's a.
It's like the integral symbol. It's like the weird form, or the partial differential symbol. It's
But
a vulgar form of an existing letter.
Yes, but this is. I don't think this is. I mean, it's.
It's
You could think of it as some form of a D, but
just
it's called
like you
nabla.
said,
Leave me alone.
There you go.
So you're going to take the gradient of f at A, dotted with v. And this formula has all sorts of beautifious consequences.
That's the same language Nabla comes
Right, that's the same way. So what do we learn from this formula? So recall, what's the geometric interpretation of dot product? Okay. So recall x dot y is magnitude x, magnitude y, cosine of the angle between them. And in particular, the biggest it can be is and equality holds precisely when cosine theta equals 1. No. Theta is 0. I.e. when vectors x and y are pointing in the same direction. So I'm not saying parallel because I mean direction, not minus direction. I mean they're pointing exactly in the same direction. Okay, so what do we conclude from this? What direction does the gradient point in?
Direction A.
Good direction.
So here you are, sitting at a point A, and you're saying to yourself, what direction should I go that direction? So if I consider different directions V, you might think of unit vectors for the moment. Considering all unit vectors V, what choice of V will make this dot product biggest?
So B is in the
Same direction as
what is that?
the gradient.
Gradient, yeah.
So in other words, if I think about all possible directions to head away from A, if I pick V in the direction of the gradient, it gives me the what? Biggest possible directional derivative. So the gradient points in the direction in which f increases at the greatest rate. Among all possible directions V I could pick, I'll make this dot product biggest when these vectors are in the same direction. So that means I've made the directional derivative biggest when I've gone in the direction of the gradient. So remember, I'm now doing unit vectors here. So this formula says when the magnitude of V is 1, the directional derivative is at most the magnitude of the gradient. And I get equality when the gradient and V are in the same direction. Do you all see why I get magnitude gradient there? Well, sure you do, because the dot product of gradient with V is magnitude gradient, magnitude V, which is 1, times the cosine of the angle between them. So the biggest I can get for this directional derivative is the magnitude of the gradient. And I get that greatest directional derivative when V is pointing in the direction of the gradient. So the gradient points in the direction in which f increases the fastest. And moreover, the magnitude of the gradient is that greatest possible rate of increase, right? The magnitude of the gradient is exactly the greatest possible directional derivative, which we just said occurs when you go in the direction of the gradient. So the magnitude is that greatest possible rate of increase, or directional derivative. So if I should hypothetically ask you on an exam to tell me what the gradient of some function is on geometric grounds, not by just calculating this, I'm asking you to reason through this. For example, let's go back to our anteater yet again. Back yet again to the infamous anteater. So we were looking at the function distance from the anteater, which was distance from the origin. And I'm at some point A, and you'll recall that the ant is sitting over here somewhere, and the big scary anteater is here, and the ant is trying to figure out how to get away from the anteater as fast as possible. So he wants to know, what direction do I move to get away from the origin as quickly as possible? And we already did the argument a few weeks ago that we should go radially to increase the distance from the origin as much as possible. What does that tell you? It tells you that gradient of f at a point A points in what direction? It's radial, right? It points in the direction in which the function increases at the greatest rate. Well, we've agreed that to get away from the origin, we should go radially outward. So gradient f at A is a positive multiple of what? Of A. So it's pointing in the radial direction. On the other hand, what is the magnitude of the gradient? So if I move radially away from the anteater, at what rate is my distance from the anteater increasing? 1. Because for every step I take, I increase my distance from the origin by the step. So change in function over change in position is 1, right? I get 1 extra centimeter for every centimeter I move. So the magnitude of the gradient is the greatest possible directional derivative. Well, that rate of change in that direction is 1, since f increases by lambda for every lambda units we move radially outward, which is radial. So therefore, we deduce from this, how do I get a unit vector that's pointing in the direction of A?
Gradient over its magnitude.
Unit, that's how I move in a positive, that's the positive multiple of A that has length 1. Right? Make a vector to unit vector. We did that the first day of class. So this is the same formula, of course, that you had from your homework problem that we used on Wednesday. We've just turned the derivative onto its side and made it the dot product, and the formula you did in homework was exactly that dot product formula. Any questions on this? Okay. So, application. So you're going hiking, and in the old days, I think they still have them, like topographical maps that you can actually get.
Yeah.
And they are definitely online too, I think now. If you're interested in hiking up Brasstown Bald or some obscure place in North Georgia, you get this map that has these level curves drawn on it that show you where the elevation is certain values, and they actually usually mark those. Right? So this might be marked at 500, and then this might be marked at 800. And then, this is probably not what happens at Brasstown Bald, but the map might have something that looks like this, where this is marked at 1,000, and then, what's going on inside here, folks?
Those two.
Well, you could have,
Or it could just be a whole.
so what is likely to be happening in here
Is different.
is that you have two peaks, perhaps of different elevations, but unless I labeled these level curves, this one actually could go back down. You could have a depression.
But it can't go lower than 1,000.
Because otherwise it would be.
Yeah, otherwise it would be. Yeah.
Well, so right. So if it went lower than 1,000, I would need another ring labeled 1,000 in there. But let's, for the purposes now, say that this is a peak that has height 1,400 here, and say 1,500 here. And we'll spend a fair amount of time soon talking about what's going on at that point. That's actually something interesting to think about. And then Eric is sitting there thinking shades of his topology class. All right, so my question to you, though, is here you are starting at this point. Well, in fact, yeah, let's say you're starting at this point, say, and you want to figure out, looking at the map, what route you should take to hike up the mountain as efficiently as possible. That doesn't mean it's going to be easiest, but what I'm suggesting is you could, for example, decide to meander around here and then walk around like this. That would not be very efficient. It might be scenic.
So straight.
So what do I mean by efficiency?
Steepest.
Greatest rate of change?
Yeah, so you want to hike uphill. How do you plan your route?
Oh, you want to get to the next, with each next curve as
So
quickly
that
as possible.
it heads, it always heads uphill as steeply as possible. So what am I drawing here? I'm drawing level curves of what function? Yeah, elevation. So at a point X on the map, these numbers are indicating the elevation of the mountain at X, or the hill, or whatever it is. Now, can you tell me, looking at this picture, what the gradient of F looks like at each point?
It's the shortest line of the next elevation?
Well, that's an approximation, perhaps. But if I'm just at this point, knowing the level curve I'm on here, can you tell me what the gradient looks like?
It like goes.
Perpendicular. So that's the first thing I want to observe now. And we're going to use this, we're going to have lots of web work to practice this with on the next round. Important observation. If I take V tangent to a level set, in this case curve, at a point A, what do I know about the directional derivative of F in the direction of V? So in particular, at this point, if I went in that direction, instantaneously, how fast would f be changing? Not at all. Because instantaneously, if this is tangent, instantaneously I'm moving along the level set, and the function's what on the level set? The same. Derivative of a constant function is a. So what do we deduce? We deduce that if you move tangent to a level set, which might even be a surface in higher dimensions, that's okay, this directional derivative is 0. It's not least per se, because you could go negative. But what do you infer from our beautiful dot product formula?
It's at most when it's perpendicular.
So if this is 0, what has to be true about those vectors? Tori, they have to be perpendicular. So from this we conclude that the gradient is orthogonal to v. Well, that makes sense intuitively. Because if you took a vector like this, surely that would not be the direction to go to increase the elevation at the greatest rate, because you're going partly along the level curve. Should make sense completely intuitively that if you want to increase at the greatest rate, you should go so that your direction vector has no component in the direction of the level curve. So therefore my gradient is pointing somewhere in the orthogonal complement of that blue vector. Common sense probably tells you it's pointing this way as opposed to this way.
Well, we don't know. We don't know that the little curve on the outside isn't up as well, no?
If it is, it could be just create a. What is it's like symmetrical at that point? What would happen?
But there's no other level curve, so just that's the wall.
So that could happen. It could happen that this was actually at the basin of a
Like a valley or something.
at the basin of a canyon, and that as you went to either side, the function went bigger. So to shut up the hecklers, I could add some more level curves and make it clear that it got lower out here. But you are right, what we're talking about today is only an approximation. We don't know anything for sure just from knowing these discrete different level curves. We would need to know all the level curves to be 100% sure of exactly what's happening. But if you'll leave me alone, I'll infer that the gradient should point in this direction. Now, I don't know from these data I have here, I don't know how long the gradient is. This is not enough information for me to know for sure at what rate the height is increasing as I go in this direction. However, you might draw some inference that you couldn't prove in a court of law of mathematicians, but that you could convince a reasonable person with. You could draw some inference about the length of the gradient here versus, say, the length of the gradient at such a point, or say, such a point. Matthias?
Isn't that like if the difference between that and the next level curve is greater, then the gradient must be smaller?
So, I think you're thinking the right thing.
Like, yeah, that distance, if that distance is smaller.
You would think that if you went something like this, you would increase 300 feet, changing your xy distance a smaller amount, whereas here, to increase the 300 feet, I would have to do some path that went longer.
Yeah.
So you would think, approximately anyway, that the rate of change is smaller here than it is here. In other words, and this makes perfect sense, I hope, the mountain should be steeper at this point than it is at this point.
Theoretically.
Now, where did the steeper come from? Something to do with your homework that people have been asking about. Well, the steepness is exactly the slope, which is what directional derivative is telling you. If you take a unit vector v, it's telling you if you move in the direction of v, and you slice the mountain in that direction, the directional derivative in the direction of that unit vector is exactly the slope of the slice. We talked about that the first day we did partials and directional derivatives. So the length of the gradient is actually telling you what?
Steepness.
Which is the slope of the mountain at that point. Right, so we have an inference here. Moreover, the magnitude of the gradient gives us the steepest possible slope of paths on them through the point A, f of A, on the mountain. And we will have on this homework that's due tomorrow and also next week, so you'll have more of this web work playing with these same ideas. If you know the slope that you're heading up the mountain, if you go in a certain direction, you actually can be wizardly and tell me what angle you're hiking uphill. Agreed? That's a two-dimensional high school trig problem. Agreed? Okay. You don't need anything fancy for that. If you know what slope you're hiking, you know the angle of elevation of your path relative to the horizontal. Okay. So, what would I actually try to do if I were a mathematician or an engineer here, if I wanted to plot myself the steepest path from here to that mountaintop? Well, I would want to follow a path that does what? Goes in the direction of the gradient or perpendicular to every level curve at each point. So I would want to plot myself a path so that as I, and in fact computer programs do this numerically, it would want to say move a little bit along this path, where's the next level curve when I get there? And as you keep moving, if you want to stay perpendicular to level curves, you're going to find that you have to take a path that veers you something like that, if you knew what all the level curves were in between. And then I would get here, I would want to be perpendicular, I would want to continue perpendicular all the way up till I got to the, whoops, that one didn't work too well. That wasn't very perpendicular. So what I drew there was terrible. Right, I would want to land here and then do something like that, probably. Now I'm going to, at this point, throw out a challenge problem, and I will give you serious bonus points for giving me intelligent answers. So you can actually turn this in as a challenge problem. Do you think that following this gradient, following the steepest route at each point as you go on the mountain, that really is the most efficient path? So, question for you to ponder: is the path obtained by following the gradient necessarily the most efficient, say shortest if you like, although it doesn't have to be that, but say shortest path to the top? Actually, the question of shortest is what differential geometry is about. Differential geometry wants to find what are called geodesics, which are shortest paths from place A to place B. I'm lying slightly, but it's basically correct. So anybody who's an airplane pilot wants to follow a curve on the sphere that will give him the shortest path. Do you guys know what those paths are? Not you.
Great circles.
Great circles. So there is a question here of, is there a shorter way to get from here to here than the route we're talking about? But in general, if I'm at each point always going in the steepest direction, do you think it really would have to lead me like that, or could, not on this map, but could the surface be such a shape that following the steepest path takes me on some ridiculous wandering path before I ever get up to the top of the mountain? So I'll let you ponder that, and you can come talk to me about it in office hours if you want.
So are we assuming that it's going to be continuous and differentiable at all points?
Differentiable function, absolutely. Yeah. Okay. So as a very simple application of this, and again, you'll get homework problems on web work next week for this. I could have been mean and put them on for today, but I wanted to make sure you had plenty of time to think about this stuff. Now we have a good way to find equations of tangent lines and tangent planes to things. What is the equation of the tangent plane of the surface e to the x, y, z squared plus cosine pi x cubed z plus y to the fifth minus e to the seventh equals. Okay, so now I'm going to cheat. I'm going to say at the point. So I want a certain point on this surface, so I'm going to cook up a point that I might like.
1, 1, 4.
0, 0, 0.
How about z is a quarter, x is 2, and y is 0.
Well, she gave us that.
Well, oh, because I need to fill in what this equals. So now I've tried to make up this point so that the number isn't too horrible. Let's see, what do I get? E to the xy times z squared.
1/16.
Yeah, it is 1/16. That is sort of horrible. So maybe, I'll tell you what, I'll put a 16 there. 1 cosine of pi x cubed z. X cubed is 8.
Or 2 pi.
Cosine of 2 pi, 1. Y to the fifth,
0.
Minus.
and then I have some horrible number here. So maybe I'll,
Change it to like.
Just take.
let's get rid of that 7. That's just silly. Let's just put cubed. And then I'll put something like an 8 there.
So this is how math.
Well, this is how problems get made up. So it's still not that great, right? That's going to be minus 1/8 now. All right. So the level set
1/7.
that this point lies on is given by the value of the function when I plug that point in, right? If I did this correctly, the value of, when I plug this point into this function, I get that, so that means this point is on that level set, where the function equals this. Okay? And I'm asking you, what's the equation of the tangent plane? Of this bizarre surface at this point.
Something like a derivative.
So who knows what the surface looks like? But I'm interested in the equation of the tangent plane at that point. What information do we have from what we've done today?
The gradient.
So we have a gradient of this function.
Is orthogonal.
So if I let the function of x, y, and z be this horrendously absurd thing, let f be this, it's certainly C1, because all these things are built out of sines, cosines, exponentials, polynomials. Those are perfectly wonderful functions. So officially I'll say f is C1, hence differentiable. Then I know that the gradient, whatever it might be, is orthogonal to the level surface. That's what we just discussed up here. So whatever this surface is, we know that its tangent plane has normal vector given by the gradient. If you know the normal vector to a plane and you know the point that the plane goes through, you know how to write down its equation. Because you did that at the end of chapter 1. So how do we find the gradient? Well, we just find it. Gradient of f at the point x, y, z is vector that has 3 partials in it. What's the partial respect to x of this mess?
16 e to the x, y z squared. Minus 3x squared pi z.
3x squared pi z.
Sine of pi x to the third z.
Okay. What's the partial respect to y?
16 s e to the x, y z squared. Plus 5 y to the fourth.
What's the partial respect to z?
2z. 16 e to the x, y.
32 e to the x, y, z.
Minus pi x to the third sine pi x to the third z. Minus 24
Minus 24
z squared.
z squared. Oh.
Evaluated at 2014.
Now we compute the gradient at A. Well, y is 0. Sine of, what was this number?
0. Well, 2
X cubed z.
Oh, it's 2 pi.
So that's a 2 pi. So this is 0, this is 0,
Yes.
0. Now, what's 5y to the fourth?
0.
But this term isn't 0.
30.
But we don't want it all to come out 0, or else you'll find out later this method fails.
2. It's just
So
2.
32, e to the 0 is 1, z squared is a 16th. So I have 32 over 16.
That's
2.
2
That would be approximately 2.
Approximately.
today.
According to some calculators.
Talk to the wizard.
Here I have 32 times 1 times a fourth.
That's 8. Mine, yes.
That's 0.
This is 0 again. And then I have minus 24 sixteenths, which is 3 halves.
3 halves.
So I have the vector 0, 2, 13 halves. Now, as fond as you are of fractions, you might prefer to say, all I'm looking for is a normal vector, so I can take any scalar multiple of this vector and use it for my normal vector. So let's get rid of the fractions. So a normal vector to our plane is going to be double this, 0, 4, 13. So what's the equation of the plane? Drum roll.
X minus x naught, or the point, plus y
But that's
minus.
times
So
0.
so we can say the normal vector dotted with x minus x of 0. So remember we're saying, remember that we did this at the end of chapter 1. We're saying if you took any point x, the vector x minus a is orthogonal to the gradient vector. So we're taking x minus a, and that dot product is 0. That's the equation of the plane.
Yeah.
Okay. Now, let me just remind you guys that you have just been doing tangent planes in a different setting. What did you just do on web work that's due right now? You had the graph of a function and it asked you for the equation of the tangent plane. That's what we did at the beginning of this chapter. We said the graph of a function, the tangent plane you get by taking the graph of the derivative as a linear map. Well, I'm now going to show you that you can do that as an application of the same formula. Important observation, and this saves you from getting confused, I hope. So we just talked about a level surface. Suppose instead I took the graph of z equals a function of x and y. Can I write that as a level surface? Can you give me a function that's constant when z equals g of xy? How could I've got a function of x, y, and z that's constant?
For some z.
G of x, y over z
Ooh.
equals 1.
X and z.
Yeah, but what if z were 0 somewhere? You have the right idea, but make it simpler than what you just did. What can I do with this equation?
G of x, y equals.
Yeah, I could look at g of xy minus z. And that function of x, y, and z will be what on this graph?
0.
So you look where f is 0, and that's the original graph. So what did we just say? We said we can get the tangent plane therefore, the tangent plane at the point, we'll say A, B, C. So this would be A, B, G of A, B. So take a point on this graph of this function, which I'm now thinking of as a level set. So here's AB. Here's the point ABC on the surface. I still want the equation of the tangent plane, just like you were doing earlier. But now I can say the normal vector in 3 space is given by what? The gradient of whom? F.
Equals 0.
So the gradient of f is going to be the normal vector. Well, what is the gradient of f? Here's the formula for f. What's the gradient of f?
G prime xy.
What's the partial respect to x? dg dx. What's the partial respect to y?
dg dy.
What's the partial respect to z?
-1.
So that's the normal vector. So the equation of the tangent plane is given by dotting that with
A, B, yeah.
and that's 0. Right? This is saying this is our normal vector. Dot it with a vector that goes from the fixed point ABC to the point XYZ, you get 0. And now write this out and look at this. I heard an O from Mallory. Partial with respect to x times x minus a plus partial times y minus b minus z minus c. And this is all 0. Equals 0 there again. Does this look like what you've been doing? Well, no, it looks totally different. What's the difference?
C doesn't have
In the stuff you've been doing, what did you do? You took this term and put it over there. And you said z minus c equals this. Well, no, you didn't. You left the c over on this side. You said z equals c plus the derivative stuff. That's the value of the function plus the linear stuff. It's all the same formula. So if you find yourself getting confused about graphs versus level sets, you can just automatically put yourself in the position of making everything into a level set no matter what, and use the one algorithm every time, rather than getting confused. Okay, so I think that's enough for today, but Monday we're going to start with one of my favorite applications of this. How many of you guys have been to the building in Washington, D.C., and I never remember what it is, where you have this gallery where somebody can, your friend can stand at one point and whisper, and you'll hear the person.
They have those a bunch of places, that's not the only one.
We're going there.
We did that.
Okay, so, well, so there's this building, although I haven't been in it, I don't think.
Let's go.
And there's a point that's marked, and you stand there and you talk in a very quiet voice, and there's people all over the place, and your friend's at this other point that's marked, and that your friend can hear every word you mumble. So my question is, what's the math that's going on there?
Microphones.